Hello, everybody. You're very welcome to our latest in our series of webinars from the Advanced Centre. My name is Louise O'Gorman, and I'm the Centre Manager for the Advanced Centre in ATU Sligo. Our theme today is the potential of quantum computing in machine learning applications. And we're delighted to have three wonderful speakers representing academia, industry, and research in this very exciting field. We have Dr. Simon Caton, who's an assistant professor based in the School of Computing in UCD, and he's going to talk to us about the journey from machine learning to quantum machine learning. We have Anton Decuzar, a research software engineer who works in one of our industry partners, IBM, and he will share his research on QML. And finally, we have Dr. Elena Blokina, assistant professor who is based in the School of Electrical and Electronic Engineering in UCD. And Elena is going to share her research with us on quantum dot arrays and qubit arrays. So before we get started in the talks, I'd just like to tell you a little bit about the Advanced Centre. The Advanced Centre is a collaboration between three higher education institutes in Ireland: UCD, ATU Sligo, and TU Dublin. It was set up in 2020, and this was in response to the Future Skills Needs report. And following that, the HEA provided funding via a mechanism called the Human Capital Initiative, Pillar 3. And what this is, the objectives is to enhance innovation and agility in higher education. So our way of doing this is that we are offering accredited modules and programs from National Framework Qualification Level 6 to 9, as well as flexible delivery via online and blended modes. And one of our overarching objectives then is to assist industry on their digital transformation journey. So we can also offer continuous professional development or CPD options as well. And one of the real benefits is that students don't have to sign up to a full program. They can take single modules, which start either in September or January. And we also have a limited number of modules which run over the summer. The core element of the Advanced Centre is that it's built around 11 thematic areas, one of which is quantum engineering and computing, and that's the focus of our webinar here today. An example of what's available in this theme is the Professional Diploma in Quantum Engineering and Computing, which is at level 9 or master's level. So you can take one core module, and then you can choose from 3 optional modules here from this list. Or you could take a single module only, if that's what you would prefer. So for further information on the quantum modules there or any of our other themes, please go to our website and follow us on social media as well. So for housekeeping, if you have any questions, which I'm sure you will, please put them into the Q&A box. And we've built in some time at the end where our experts will be able to answer your questions. So without further ado, I'm going to hand you over to Dr. Simon Caton. So from the Advanced Centre and my colleagues, please enjoy the talks.
Thank you, Louise. Is that okay? Can you see everything?
Yes, that's fine, Simon.
Okay, perfect. So just very briefly about myself. My name is Simon, as I was already introduced. I have a PhD in computer science. I'm not trained in physics. I don't really have a physics background. So from that perspective, we thought it would be nice to maybe talk a little bit about, well, for someone who doesn't necessarily have a physics background, what sorts of pathway could you expect from knowing something about machine learning to trying to learn something about quantum machine learning? So if you bear with me, this is going to be a bit high level. It's also going to be quite quick, but I'm going to give you a hopefully reasonable overview of machine learning on the assumption that you might know something about this already. and then talk primarily about the main differences between machine learning in its classical sense and what happens if you add quantum computing to this. And then finally, some small resources that you can either use for structured education through advanced, or if you just want to learn a little bit more by yourself. So essentially, what is machine learning? The idea is to take some sort of data, in this case, a handwritten digit of the number 7, extract some features from that we can use to build a model, and then use that model to perform some task. In this particular case, it's to recognize that this handwritten digit is the number 7 and then output a 7. Now, that's of course that's a highly oversimplistic view of the world, but hopefully this is not something that's too alien to you. Now, even though this is the general sort of idea of take some data, build a model, and do something with it, there's more than just classification or the emitting of a label, in this case, the number 7. So in general, you can imagine that there's 2 main schools of machine learning, which is the supervised case, where you have some clear objective and ground truth. So for example, with the picture of the cat, I can tell the model in advance, this is a cat. And if I provide it with enough examples of a cat, it should hopefully be able to learn to recognize a cat. This is classification, it's supervised machine learning. In the middle, we have an example of unsupervised machine learning, which could be where I don't have a ground truth, which would be something like trying to identify different types of customers in my customer database, or finding patterns, or trying to find things that are somehow related in a meaningful way. On the right-hand side, we move into another form of supervised machine learning, which belongs to the more statistical focused side of things, which is trying to predict a numerical value, or to, in this case, forecast revenue over years. The difference to classification, in classification, I emit a concept like cat. For regression, I'm emitting some continuous number like a price. The one down the bottom, which is probably then the last most well-known form of machine learning, is this idea of recommendation. And you've interacted with this probably on a daily basis if you've used any online store. I've searched for a book. This book, by the way, is going to come up again at the end. And these are the books that other people read if they look at that book. And it's this idea of recommendation. So it's finding patterns within the data set in order to make some suggestion. Okay. What I want to do very quickly is just outline the general machine learning process so that we can then map in, well, what changes with quantum machine learning. So this way of presenting it might look a little bit unusual, but it will hopefully make sense when we come back and say, well, this is what happens if we add quantum to the process. Essentially, we can view machine learning as 3 things. We have some data, we have to prepare it. Okay, this is this idea of pre-processing data. There are some things that we would typically do there. We can see those on the slide. The important part here really is this idea of understanding the data set and preparing it for generating a model. In the middle, we typically try to fit or to learn something from the data so that we have a model that represents that data in some way. Typical activities here would be things like trying to optimize the fit of that model, so how well it represents the data that it's been used to how well it's trying to represent the data that's been used as training, if it's a supervised case, or if it's something like clustering or pattern recognition we saw on the other one, or on the previous slide, how well it represents these different types. And then finally, at the end, we produce some sort of outputs. This could be groups of data in the clustering case, or a value or of some sort. And here we also would evaluate the quality of our model. In general, this is quite simple. When you present it like this, there's a lot more work that goes on behind the scenes, but this is the general sort of series of steps that we would do. And now the question is, what happens when we add quantum to this? Before we can do that, we need to talk a little bit about quality, because Anton will come back and touch on potentially parts of this in a moment. Typically, what we do is we measure the difference between what we would expect to get and what we actually got. And on the basis of that, we can derive some notion of performance or quality. You've potentially seen this a lot before. I won't go into it in too much detail, but the idea is that there's some sort of quantitative way that we can assert the quality of a model that's being produced. If we instead now say, okay, what happens if we add quantum? So the first thing that we have to do is we have to realize that in machine learning, we typically work in Jupyter notebooks or similar. We can still do that with quantum, But we have to realize that there's a conceptual difference between how a quantum program works and how we program a deep learning or a deep neural network. And this really comes down to this idea of quantum gates, if you have a gate-based approach to quantum computing. And these gates represent essentially forms of quantum operations, or operations that the quantum computer knows how to do. There's also some differentiation here between the quantum part and the classical part, in the sense of when we observe our quantum state, that there are certain specific properties that we need to keep in mind and be aware of. But the important thing is that there's a conceptual difference here between writing lines of code and the quantum circuit that the quantum computer will execute that we have to do. The nice part is that we can still write all these things in Python, and they can be converted into these kinds of programs for us. The other thing that's very important is this idea of data. So data is quite different on a quantum device. Typically for machine learning, we have some sort of well-structured data that we understand and that we can look at, but this is not really the case for a quantum device. We have to transform our data, if it's in a classical context, into some quantum representation, which is more the line of which Anton is going to be talking to you about. Or we may have some experimental output from a physics or quantum mechanics experiment that we then want to try and fit a machine learning model to. We're focusing mainly here on the second one of these, of I have a quantum computer, therefore I need to put my data into a quantum representation. Okay, what I've tried to do now is put the bits in red that have changed from what we saw last time. So in our pre-processing step, we now see there's one new point, which is this transformation from a classical representation of data into a quantum representation. This is actually a very, very hard problem, which we will come back to a little bit in a moment. After this, the bit in the middle, of course, is where you'd expect most of the change to occur. So we're trying to fit a quantum model to quantum data. This will typically be looking like a circuit, or the circuits that we saw on the previous slide. We may still have some form of classical optimization to tune the algorithm or to tune various parameters of our quantum algorithm. We still have this idea of performance that we had previously, but then something else happens. So in order for us to be able to come up with some meaningful output, we need to observe the quantum algorithm or the quantum model multiple times in order to generate some kind of probability distribution with regard to the output that's being emitted by this quantum model. This is something that can often be very, very easily forgotten and overlooked, but it's essentially part of the process that can increase the cost in terms of using the quantum device. It has to work a little bit harder to generate all of these different observations. The other thing that might be worth mentioning here is a very common approach here is to use what's called a variational algorithm, which essentially means that these gates or these quantum operations are parameterized. And it's those parameters that we tend to tune with a classical optimization method. Finally, we then have our quantum model. It produces some output. This output is in the format of a bit string. This bit string corresponds to the observed state of each of the qubits that we have. And from that, we need to map that into some classical representation that we can then understand as, this is a cat, this is not a cat, or here's a number that's being forecast. So in terms of the whole process, we have some pre-processing that may happen classically, a transformation into a quantum representation of data, the fitting of that model, potentially with a classical optimization routine, a quantum representation of the output, we transform that to produce the output that we can then do something with, and we're back then into a classical scenario. I'm aware of time, and I'm also going very fast, and I apologize for that, but I want to give you just a bit of a flavor before we go into some of the more details. There are, however, some pretty difficult challenges here when we want to do things like quantum machine learning. You can imagine that this input and output transformation is actually very, very hard. There's a lot of work just going into how do I correctly prepare my data for quantum machine learning, and how do I correctly interpret the output of the quantum model. Similarly, the design spaces can be very, very large. And that corresponds to what's called the costing problem. And finally, this idea of defining better is quite difficult. So you've probably heard this term of quantum advantage. defining that word advantage is actually not so trivial. It doesn't just mean that the accuracy, for example, is better. It can mean many, many, many other things. Okay, and that definition can be quite difficult. So finally, just to leave you with a small flavor of, well, okay, I find this fascinating, or I don't really understand it, but I'd like to know more. What can you do in order to try and get into the space of quantum machine learning? So the very first thing that I would say is, if you don't know machine learning, this is going to be a very, very uphill struggle. So that your first port of call would be to learn classical machine learning. Trying to come straight into the quantum machine learning side of things is going to be a very, very steep uphill battle. Some familiarity with quantum mechanics is useful. And so the two pictures on the left here, one is a podcast from the University of Oxford. It's a very, very nice podcast. I would suggest to watch it with video, not just listen to it in the car. The Theoretical Minimum by Leonard Susskind is also a very nice read. And then on the right, we have a general introduction from IBM into Qiskit, which is their quantum development environment. And the book on the right is personally one that I'm basing a quantum machine learning course around. And it's a very nice read. Of course, there's also some resources available from Advance, which Louise has just mentioned to us. And really, it's get your hands dirty, get going, give it a try. Try and do some problems that are simple. Take something from classical machine learning, try run it on a quantum computer in simulation or through the IBM Q network, and see what happens. Otherwise, that's it from me. If you're keen on the books, I'll leave the slide here just for a second. But otherwise, yeah, I will hand over to Anton, who's going to give us a much more in-depth view of quantum machine learning. So Anton, over to you.
Thank you very much, Simon, for a great introduction. I hope you can see my slides. And yeah, so we're going to dive slightly deeper. So yeah, first of all, I'm a research software engineer from IBM Research Europe, based in Dublin. My background in applied mathematics. I don't have physical training as well, so sometimes it is easier for me to understand, to look into quantum computing from a pure mathematical approach. But yeah, as Simon mentioned, physical background is very essential. So let's get back to quantum machine learning. We're gonna talk about what we can do and what is already available, say, in quantum machine learning. So first of all, we can consider how our data may be represented and where we can process our data. Basically, on the left-hand side, we have 4 blocks where you have first letter is data representation, the second letter is processing, right? And we are going to talk about this square where we have classical data and quantum processing of our data. Basically, we have the same approach as Simon presented. We have some training data, then we have our model. In our case, it should be quantum because we are talking about quantum machine learning. Then we have a loss function or a cost function. Basically, this is the way how we may assess how good our model predict unseen data or predict on unseen data. And then we have to, of course, optimize our model somehow. And that is why the very usual approach is to apply a gradient descent algorithm. And that is why we have to compute a gradient of our loss function with respect to our parameters. As we saw before, we may have parameterized circuits where we have some parameters, and in the end, we want to optimize them. So this is our, say, a very common loop where we start from our training data and we end up having a quantum model, right? So how can we build such a model? So we have data, then we have to apply data encoding. You may find out that it's called sometimes feature map or embedding. So basically, this is the way how we convert our classical data into a quantum representation. Then we apply our model, and then we measure the outcome, and we have to convert our quantum, say, results into a classical representation again. So this is our circuit, right? So we have E of X. This is our data encoding. This is our feature map. In other words, we have actually our model in between U of theta, where theta our set of parameters we want to optimize. And in the end, we get Y hat. This is our predicted value. And we want to compare this value against ground truth. So this is what can be done in classical way. Okay, so first, a very important step, data encoding, right? So imagine we have a vector, x1, x2, and so on. And we have to, this is our classical data, right? There are no qubits, there are just bits here. And we want to load this data somehow into a quantum computer. So how can we do that? So there are different ways. The easiest one is just to convert our data into a binary representation and encode one single bit in this representation to a one single, say, element of our state. So basically, we should have the same state as we have as a binary representation of our data. It's easy to do, well, but it requires n qubit for n bits. Okay, it's okay, but sometimes we can do slightly different things. We can apply amplitude encoding. So basically, in this case, we need a logarithmic number of qubits for n classical bits. So this is a very, very interesting approach. But the problem is that loading is really difficult. So you trade time to space. So instead of having a lot of space required for your data representation, you need a lot of time to encode such data. In this case, each element of your vector is mapped to a single basis state available in quantum computers. And we have the third way, perhaps the most common one, angle encoding. So as Simon said, we have different gates, we have different operations, but mostly all of them are about rotating a point on a unit sphere. So basically, once you have your data in a quantum computer, you may say that your qubit is a sphere, is a unit sphere, and you choose a place on this unit sphere. And this is the way how you encode your data. So we may apply such rotations, and we also make use of entanglement or C-naught operations to be sure to capture dependencies or to capture some patterns between different bits or qubits in our data encoding. So yeah, this is a very good encoding, very interesting one because we make use of entanglement, but we still need n qubits for n bits. So the next step is to choose ansatz or model. Before that, it was U of theta. And this is our circuit that should be trained. And this is what we get in the end. So we have a complete Hilbert space here. Our ansatz, depending on the parameters it has, may cover just a small portion of this Hilbert space, right? And that is why it may cover the solution or may not. And depending on the ansatz, especially it should be designed in a way that it is efficient with the hardware available, for instance. you may get, say, a global optimum, a global optimal solution, or you may end up having a local minimum, and that would be also a solution, but it may be not optimal. So choose of ansatz is very important, and depending on the ansatz, you may get either good or bad solution, right? And you may try to guess which ansatz is better in this case. You may run a few different models, and in the end, you choose one of them. For instance, if you know that the output is, say, has just real numbers, then you may try to apply a real amplitude ansatz, right? So how do we measure and how do we post-process the outcome from quantum computers? So they are probabilistic by nature. I mean, the quantum computers. So that is why, in the end, the simplest way is to measure just bit strings, right? And you may have, as shown here, for example, 0, 1, 0, or you may have 0, 1, 1 as an output. And to be sure that you captured the right outcome, you run your circuit for many times. We call it shots. And then you may come up with a distribution of such bit strings. And as shown here on the plot, we have more outcomes where we measured 0, 1, 0 rather than 0, 1, 1. And then we may just map the number of ones in this bit string to our label, to our class. So for instance, if we have even number of ones, we may say this is our dog on the image, right? If we have odd number of ones, we may say this is a cat. And this is the way how we transform our quantum data, quantum outcomes into a classical way. Another option here is to apply expectation-based post-processing. I'm not going to talk about what it means in details. Basically, you just measure a quantum mechanical observable. But to be simple, we have a single number in the end that spans the interval from -1 to 1. And then you may just choose how you interpret this value from -1 to 1. For instance, you may apply a sine function. And if you have a positive number, this is our dog on the image. If you have a negative number, you may say you have a cat on your dog. So this is the way how you may map your expectation value to a label. And this is our predicted label in this case. So these are two common ways how you may post-process your data. Of course, there may be different variations and you may apply different techniques, but in general, you may either have a set of samples or you may have an expectation value of a quantum mechanical observable. Okay, so so far so good. We have this loop, but the problem is that if we want to apply optimization techniques, we have to compute gradients, basically, of our cost function. And since the model is quantum, we have to evaluate our gradients on a quantum computer. It is still possible. There are different techniques, but in general, it can be done. If you're interested in this technique, you may Google for parameter shift rule. It's a very interesting technique how you may apply, how you may estimate gradients of a parameterized quantum circuit. Quite simple and quite powerful. All right. The next topic, what I wanted to cover in this brief talk is quantum kernel. So what can be done here? Let's get back to a classical world and support vector machines. We're going to have a very simple problem setup. We have two classes, blue and red dots, our cats and dogs, and we want to classify a new dot, whether it is a cat or dog, right? In case of support vector machines, we want to have a hyperplane, or in case of two-dimensional data, this is just a plain line. And we want to maximize the margin between the hyperplane or line here and the dots on the top and on the bottom. So this is a very well-known machine learning method, and we just want to update it and apply quantum. We want to think how we can do that on a quantum computer. The biggest thing is that we are not usually work in a original data space. We want to apply a kernelized SVM. So on the right-hand side, you see blue and red dots, and there is no way to draw a line between those two classes. But if we introduce a feature transformation into a higher dimensional space, we can do that. So we want to introduce a kernel that is an inner product of our mappings to a higher dimensional space. So instead of working in our original data space, we work in a space where we map our data points to that space. And idea here is that to reformulate the SVM problem in a way that it depends only on an inner product between points in that higher dimensional space. So for instance, we may introduce a feature map here where we take the same coordinates x1, x2, and we add the third coordinate, that is x1 squared plus x2 squared. And in this case, we may have a circle here. And if we consider that in 3D space, we can easily see that there is a hyperplane that separates blue dots and red dots. And this is the way how we may train a kernelized version of support vector machine in classical representation. So what is quantum SVM in this case? We have Hilbert space, and this is exponentially large Hilbert space. So idea here is to compute our kernel on a quantum computer. It can be done. So in this case, we introduce a transformation, or our feature map, or our embedding, in other words, same as it was before. But here, we don't train our circuit. We only evaluate our inner products between different points of our, or samples of our data set. And in this case, we end up having just a very simple circuit where you apply a feature map and then you apply an inverse feature map. And in this case, you supply x and x prime, and you estimate a value, an element of your kernel matrix for these two elements, x and x prime. And this is the way how you basically compute quantum kernel. Once you have such metrics computed, then you apply a classical support vector machine and you get your model trained. Okay. Is it really all of that bring quantum advantage? So far, this is an open question, and in a very special setup where you have a very special artificially generated data set, it is proven that you may get exponential speed up over classical methods. But as I said, this is a very special case, a very special data set, and it can be generalized to all possible data set. But hopefully in some time, we may get better models better understanding how we may train a quantum machine learning model. So that's it from my side, and I hand over to Elena, who will talk about her research.
Thank you. Can you see a full screen?
Yeah, all good.
Sorry, a couple of adjustments. All right. Okay. Thank you, Anton. When we were brainstorming the ideas for the content of this event, we thought that we should talk about one example of quantum hardware and show the connection between quantum algorithms and qubits. So this is what I'm going to do. I'm going to talk today about quantum dot arrays and quantum and qubit arrays for quantum computation. So when you see an example of a quantum circuit, we've seen this like from the previous talks, horizontal line means a logical qubit, and a block on that line means a single qubit gate. And a symbol connecting two lines, or like maybe even more horizontal lines, means a two qubit or multi-qubit gate. You often see a quantum circuit expressed in terms of, my apologies, actually, the wrong slide. You often see a quantum circuit expressed using Pauli gates, Hadamard gates, parameterized rotations, and CNOT, which is a quantum version of a controlled knot rotation, controlled knot gate. In some cases, you may encounter a block acting on multiple qubits, which is usually just a generic unitary gate. So this diagram implies that there is a physical system that realizes required number of qubits, and there are two or more qubits connected together, so we can implement many qubit gates. So you may ask a question, what physical system realizes a qubit? So what actually is that quantum mechanical system that implements a qubit? And even more, how many qubits, so how many physical systems we need to place together, and how we control their states and the interaction so we can actually run a quantum algorithm. So one of the examples I'm going to focus today is based on electron spin. And I want to highlight, by the way, that there are many other examples of quantum technologies and qubits, but today, like, we're just talking about quantum dot arrays and spin qubits. So a qubit is a quantum mechanical two-level system with two distinguishable states, basis states, 0 and 1. And you may recall from a university course or school course that electrons possess charge, but they also possess spin. So spin is a form of intrinsic property that once you measure, always results in only two possible outcomes. The spin degree of freedom of electrons naturally defines a qubit. And like we say, it's a spin up or spin down basis. Again, if we just use like one particle. So it's something that's already available to us, and it's very natural to use electron spin to define a qubit. So what is also useful is that Pauli quantum gates used in quantum computation are connected directly to spin operations in quantum mechanics. So in order to realize a qubit, we must trap or confine an electron in unmanipulated states. However, at room temperature, in solid-state materials, electrons do not display individual quantum properties. In order to force an electron to behave as a quantum mechanical system, we can use a concept known as a semiconductor quantum dot. A quantum dot is a very small island or area in a semiconductor material that is controlled quite precisely by electromagnetic field. It is connected to what we called electron reservoirs, sources of electrons, so we can just take one electron from that reservoir and we can place or allow this electron to tunnel from reservoir to a quantum dot and stay in that quantum dot. So now all of that is cooled down to extremely low temperatures, and in some examples it's as low as 100 millikelvins, just because we isolate the system from thermal energy, from thermal fluctuations of atoms and electrons in the host material. So we just want no thermal noises in this case. Once an electron is trapped or confined in a quantum dot array at a very low temperature, it displays quantum properties. So we can send a pulse of electromagnetic field and we can change position of an electron, or we can change the spin of an electron. So if we manipulate the position of an electron, we say it's a semiconductor charge qubit, and if we manipulate the spin of the electron, we can say it's a spin qubit. Now, I will show you some examples of semiconductor quantum dots. So again, structures used to implement to realize qubits. And you can see, again, if you're interested in this, you can see there are references and literature sources from where these examples are taken. Firstly, there is this nice visualization concept. You can see there is a host semiconductor material, and there is a structure of metal gates that exerts an electric field into the semiconductor material. So we can see some local wells of potential energies, potential energy forming there. So these local wells will confine electrons. If we send a high-frequency electromagnetic pulse to a quantum dot, the spin of the electron will be driven to a superposition state. So if you use a spin as a qubit, so it's now in a superposition state. So in terms of a qubit, it corresponds to a rotation of the Bloch sphere along the longitudinal line, or we can kind of say it's a parameterized X gate or parameterized or Pauli quantum gate. If it do not drive electron with a high frequency pulse, just allow it to evolve, to experience quantum evolution, quantum dynamics, it experiences a precession on the Bloch sphere along the latitude line. So, and again, if you would consider the system as a qubit, so it means there is a Z kind of type of rotation or parameterized or Pauli Z or kind of parameterized rotation. Now, if you recall, a quantum circuit would require many qubits. So, usually we want as many as possible with quite high quality, high fidelity qubits. But it means that quantum dots must be arranged into a structure. It's a one-dimensional or two-dimensional structure known as a quantum dot array. For simplicity, we can say that each quantum dot will confine one electron. So if we use spin to encode quantum information, so we can just say directly it's a qubit array. Semiconductor materials and technology allows us to design such structures, and you can see there's quite many examples known, and I just choose some examples here. So a quantum dot array could use in principle different semiconductor materials, but like one common example would be silicon, one of the most common semiconductors available. There are also combinations of materials, for example, silicon germanium structures as well. We can find such examples. So the idea here that dots arranged in a one-dimensional structure. So now we can place electrons, we can manipulate spin, and most importantly, we can control interactions of electrons in those structures. Interactions between electrons in a quantum dot array is extremely important, because that's how we actually generate two qubit and many qubit gates. Most important physical mechanisms allowing spin of electrons to interact is exchange interaction, and it results from a combination of effects, and we can control this type of interaction, so we can kind of suppress it, or we can enhance it by adjusting tunneling barriers between quantum dots. Exchange interactions is responsible for entanglement between qubits, and that's the mechanism to achieve two qubits entangler gates. For example, controlled Z rotation or controlled X gate, or any other actually two qubits or many qubit gates that's supposed to result in entanglement. So as a result, we will have a specific sequence of pulses, high-frequency pulses, to control single electron and single gates, but we also will have a specific sequences of pulses to generate or to induce two election or many election interactions. So therefore, like in this concept, if we want to use a gate-based computation, so every gate will be defined by its own specific sequence of pulses implementing the gate. And let's say we have this qubit quantum dot array or qubit array. So we know how we can connect qubits. So what's next? We can use this actually in two different ways. For example, if we want to implement an algorithm, like where we need a sequence of let's say universal gates, so we can do the following. let's say we know we need like a specific rotation, parameterized rotation, next rotation. So we apply a specific pulse to one qubit. Then we apply another pulse to another qubit. Then we say we want to implement a CNOT gauge. So we will kind of apply another sequence of pulses to entangle 2 qubits, and then another qubits, and so on and so on. So as a result of this sequence, we are going to implement like a more, let's say, conventional form of a quantum circuit, quantum gate pace circuit. So where we will see a combination of single qubit gates and 2 qubit gates. But alternatively, for example, we can consider let's say another approach. Instead, we can consider dynamics of one electron or group of electrons, or maybe the entire quantum dot array. So we call this evolution by a Hamiltonian operation. So if we know what's the energy of the system, if we know what pulses and kind of fields we apply, we can derive the energy of the system, and we can actually introduce. We can consider this as a Hamiltonian evolution gate. So in this case, you will see a symbol like this. So it just like means a unitary evolution. Now, having said this, the question is like, what's the outlook and the research question? So what are the interesting problems to solve and kind of, to investigate? And if you are interested in physics and engineering aspects of quantum computation, then there is quite a lot of research questions and research tasks. So there is, by the way, quite significant progress made in understanding materials, controllability, scalability, how to build one-dimensional and two-dimensional arrays, and so on. But there's still quite a lot of research on materials. So there is a very interesting ideas how to design 2D and maybe even 3D quantum dot arrays. And there is a very interesting ideas on how to design algorithms which are hardware aware. So which are most efficiently work on specific configurations of quantum dot arrays. Now, if you are, let's say, more interested in the software and kind of algorithms and machine learning side, there's again also quite many questions there. For example, what we're interested in our research group is to understand if we can use quantum dynamics of many qubits or Hamiltonian evolution gates for quantum algorithms. There are a class of algorithms where we believe it's actually quite good, and we will perform well. And for example, we would like to know if you can compare, let's say, more conventional form of an algorithm using universal gates with Hamiltonian evolution gates. So we would like to understand what's the best structure of a quantum circuit for a given quantum dot array. So can we use, in what algorithms quantum dot arrays by Hamiltonian evolution is again more. So what are the important, for example, expressibility or entanglement properties of different evolution operations? So how we are going to affect algorithms and so on. So I'm going to give credits to, let's say, some team members, Niall and Angie, who actually have done a lot of work to understand variational algorithms and their connection to evolution operations. So, but overall, there is many interesting research topics and questions, both on physics side, on the hardware side, but also on algorithms, and in particular to make them aware, like to make them hardware aware algorithms. That's it, and thanks for listening.
Thank you, Elena. There were 3 really interesting talks there. So if you want to stop sharing your screen, yes. Elena, I'd like to invite Simon and Anton, our 2 other panelists, back if you'd like to join us there, Anton. And I'm going to hand over the baton to Simon now, who has been monitoring the questions coming in and will engage with the other 2 panelists to answer those questions. So I'll hand over to you, Simon, who's about 10 minutes.
Thanks, Louise. So just while people are still considering what questions they might want to ask, do remember to please put them in the Q&A box. There are still a few participants that have a raised hand. If you type it into the Q&A box, and then we can put it to one of the panelists. I might just start with the question that's I suppose probably key to this type of scenario. And Anton, if you're okay, I'll put this one to you for the moment, which is, we've spoken mostly about supervised learning so far. What can we do outside of the supervised learning space? Can we do anything in unsupervised learning yet with quantum techniques?
Thank you for the question. Yes, we can. Well, first of all, in Qiskit machine learning, we have quantum generative adversarial networks, for instance. I don't know if we can call them kind of unsupervised learning, but yeah, this is the way how we may, for example, learn a probability distribution. So this is an example that we have in our tutorial available in Qiskit machine learning. So basically you have an unknown distribution and you want to learn it. So this is one aspect of generative adversarial networks. I don't know if it is called kind of unsupervised learning. I would say it's mostly semi-supervised, or you may consider them as a dedicated stream. Another thing, for instance, you may find on the internet a quantum k-means, a clustering algorithm. But you should be careful with such things, especially in case of quantum k-means, because this algorithm in particular relies on quantum memory that is not yet available, and I'm not sure it will be available. So in case of IBM, we are mostly focused on algorithms where we may at least consider that we may get quantum advantage in near-term future. When I say near-term future means, I don't know, years. It's not about months for sure, but years, and maybe 5 years, 10 years, I don't know. We'll see. And especially in quantum machine learning.
Okay, so thank you for that. Actually, the question I was gonna put to Anton to you next has actually just been asked by a member of the audience, which is, can we tackle real life problems, or what practical applications might there be for QML, either at the moment or over the forthcoming future, or in the forthcoming future?
Okay, this is a very good question. Well, I would say quantum machine learning is still kind of a very young area, and we are playing with tiny and toy data sets. I don't think we can tackle really large ones that you may find, I don't know, on the internet everywhere, right? But for instance, yes, we have another tutorial. I'm getting back to this, topic where we show how to train a classification model on a very well-known iris dataset. I think this dataset is so popular that every machine learning scientist or engineer knows about it. And this is a very good example that we start tackling problems that are small enough, but once we grow, I think in the end we may tackle real life problems, but it's going to be a long journey anyway.
Yep. Elena, there's an interesting question that's just come in relation to one of your slides, which is, would you be able to explain what does it mean for an algorithm to be machine aware?
Yeah, okay, I guess it's a hardware aware or kind of machine aware. So, okay, I can explain it as follows. For example, if you work with a logical qubits and you design a quantum circuit, so in principle, you can kind of place single qubit gates, 2 qubit gates, like many qubit gates in any place in the circuit. However, not all qubits are physically connected. So sometimes you may have like a CNOT between, let's say, qubit 1 and 3, but like in the actual realization, qubit 1 and 3 are not connected. So, and then it means that there must be some intermediate step to, let's say, remap or redesign your algorithms and use some other intermediate operations to achieve entanglement between the qubits, again, which are not physically connected. And in this case, you may even ask, okay, so but it takes from a coherence, it takes from actual performance and from fidelity of the performance of the algorithm. So you may ask a question, if I know an actual connectivity or kind of interconnect map of qubits, maybe I can design an algorithm that actually utilizes these connections much better in a more efficient way, so we don't have that many intermediate operations we don't need. So that's probably like one of the obvious, let's say, examples of a hardware-aware algorithm. And also, maybe I'll add a little bit more. So there are different types of 2 qubits and entangler type of gates available for different hardware. Sometimes you can use a CNOT because it's one of the universal universal gates. But sometimes you actually have a different type of entangler, which is nature for kind of, let's say, normal, okay, for given hardware. So maybe you can think of an algorithm utilizing a control Z or swap kind of type of entangler instead of CNOT, and see maybe again that will be more efficient in hardware.
So essentially, I suppose to summarize, it's when the algorithm has some understanding of the limitations of the hardware. Or we shouldn't anthropomorphize things here, but where there's an understanding of the limitations of the hardware or the features of the hardware, this is incorporated into the design of the algorithm itself. Anton, I'm going to come back to you again. There's another question here that I really like. It's one actually I wanted to ask. So I'm glad it's come from the audience, which is, okay, for somebody maybe who is very, very new to this idea of quantum machine learning, what's the potential advantages? Like, why should somebody learn this? What are the sorts of things that could come about? What benefits could there be from learning and eventually deploying quantum machine learning models?
Okay, yeah, another good question. So honestly, right now, there is nothing interesting that can be done in quantum machine learning from a practical standpoint of view. You can do the same with classical machine learning, faster and better. But as I said, we are on a long journey, and hopefully we may reach quantum advantage. And for instance, what I shared on the slides, that quantum kernel methods may be very promising. And as it was shown in the paper, that for a very special, very artificial data set, you may get exponential speed up. So basically, in this case, you cannot capture the patterns from your data in a similar way that quantum computers do. You cannot do that classically, or it's going to take a lot of time to train such a model. So that is why maybe kernel methods are the most promising technique to get some advantage from quantum machine learning. And here we get back to a original problem that was shared many times during the webinar, that we have to know how to map our classical data into a quantum representation. And this is the key, I would say, because if we get back to quantum kernels, we only use actually this mapping, and we compute a kernel values out of such embeddings, mappings, feature maps, whatever you call it. So this is the important one, the important step, very important one. And then kernel methods, perhaps they are the most promising.
I'm keeping half an eye on time, so maybe just put one last question, and maybe we could put this to all of us. Anton, I may, as you've just finished, I may put this one to you first, and then we'll move to Elena, and then maybe I'll finish it up at the end. And the question, for someone who's looking at this sort of topic and thinking, okay, this is great, but where do I start? So, Anton, I was wondering if I put to you, how did you get into this space? Like, what was the journey that you went through to be sitting here as a quantum machine learning person?
Okay. I've been working in quantum computing for 2.5 years. It was a tough and long process of learning the things. Yeah, the only one way to get there is to read, try to understand, try to, to run simple examples, and so on, so on. And I totally agree with Simon that the book by Maria Schultz is the best book if you want to be in quantum machine learning.
And Elena, what was your own sort of path into all of this?
Right, I approached it from a different side, from actually physics perspective, because I'm absolutely fascinated by I mean, like, by quantum properties, in kind of in semiconductor materials, and in particular because also I have a background in electronic engineering. So we can use transistors to confine electrons, which is transistors, the same technology you would use. I mean, like, in regular electronics. So yeah, I mean, like, my journey is from physics. Okay, so it's like creation, kind of, building confinement systems, control, and yeah. So.
I mean, for me myself, I started as in the machine learning space. Had a conversation over coffee once about, well, what would happen if you applied quantum to this? And that was 3 years ago. Now having read a lot, as Anton said, reading is your best friend. It's trying to generalize and come up with an understanding or familiarity, let's say, with some of the topics that are foreign to us. Louise, I think at this point I should hand back to you.
It's just perfect timing, Simon, and thank you so much for hosting the questions there. It just remains for me to thank you, the audience, for participating in our webinar today. We appreciate you giving our time, and most of all to thank Elena, Anton and Simon for their fascinating insights into their own journeys, and from the academic side, where Simon is developing and teaching courses on quantum. Anton is in the industrial side, and then Elena was sharing her research with us. So I think you'll agree that the coming years there's going to be a fascinating advancement in this area. So I think if anyone is interested, this is a great opportunity and a great time to get involved in quantum computing and quantum engineering. So if you have any queries, please come and talk to us, and we can either connect you in with our panelists today, or we can give you advice on some of the academic and programs that you could get involved in. So thank you very much, and I now close the webinar. Thank you.
Thank you.
Thank you.
Thank you.